In the last two lectures, we have seen that Poisson brackets help us describe the system dynamics in a relatively simpler way. So we would like to also see some examples of the usage of Poisson bracket. If you go back to the lectures where we proved some theorems on the Poisson bracket, we arrived at some expressions which looks like and where g could be any function of q, p, t in general. Now, remember our Hamilton's equation of motions. So we have the first equation qj dot to be equal to del h del pj. Now, since this above relation holds for any g, it should hold for Hamiltonian as well. So in that case, we should be able to simply write, and similarly for pj dot we have so you see, when we use Poisson bracket, our equation of motion for q and p, they look identical. So it has very convenient form. We can simply write that for jth independent coordinate, let's say eta, it could be q or p. This is conveniently represented by this equation. So it looks like our new form of the equation. I mean, it's basically Hamilton's equations of motion, but written using Poisson bracket. The advantage is now it has a simple form. It looks very close to the quantum equations though. So now we have this result. Let's look at some example. For example, for a 1D system, suppose we would like to calculate a quantity like this. We are calculating Poisson bracket between q and p to the power n. Well, we already know that q and p, this gives us 1. So we can use this result to calculate qp square, and that would be equal to q. We write p square as a product of two p's, and then using the product rule, because qp is 1, we simply have simple. If we extend that to qp cube, then of course we use the same trick to get in general. I mean, if we proceed, you would be able to show without much difficulty that this should be a standard result that we will often use. What about something like, how much would that be, a Poisson bracket of that kind? Well, of course, you can simply say that we use the previous derivation for n, and then we are tempted to replace n by -1. But there are still other ways of looking at it. Let's try that. You see, we already have this result. The Poisson bracket of q and p is equal to 1. And that tells us that we can simply write it as but the left hand side, using product rule, we can say so. Now qp square, we already did that, and that was 2p, and so the p's cancel and we have p square q to 1 is equal to -1, and that gives you a result that you possibly suspected already. Okay. Another problem that we use for practice is, suppose we are given a Hamiltonian of this form and a dynamical quantity which is half of pq minus h times t, t being the time. The question is, so we are asking the question whether d is an integral of motion. So obviously we start with our standard formula. First time we wrote it, we had some subscript here, and later we proved that certain subscripts not necessary. For, any canonical variables that you choose, the Poisson bracket remains invariant. In any case, let's say work it out. We substitute everything to find out that we will have half of p, q and h. So basically this term and h, and then minus ht and h, another Poisson bracket, and the partial derivative of d with respect to t simply gives us minus h. Now you see this second term, this is 0. T is not a function of q and p, it can be taken out of the Poisson bracket, and Poisson bracket of Hamiltonian with itself simply vanishes. Then what we have is the first term. The first term we write it down as we are using the product rule. And then of course we'll have to calculate QH, which is equal to the first term is straightforward, we did it before. So it is just 2 times p, and this 2 cancels, so we have p from the first term. And what about the second term? The second term, let's calculate it. We do this trick that we did before. We note that this is 0. and then we rewrite it as, but then this equation gives us, if we use the product rule, now this second term is 0, because if you use the product rule once more, you will be left with Poisson bracket of q with itself, so which vanishes. So that means this term is 0. So if that vanishes, then there is only one other possibility for an arbitrary q. This must vanish because the right hand side is 0. So we have if you carry it out one more time, the same trick, then we shall see this is 0. So which means this term is 0, and we have from q and h simply p, nothing else. Now we will focus on p and h. So we want p and h, and that would be the first term of the Hamiltonian, p square by 2, and the first term is 0. Using the product rule, we can see that. So we will focus on the second term. So p by q square. Now, how do we do that? We'll use the same trick. So that means you write down -1 and then rewrite the left hand side as this, and then you use the product rule, which will give you -1. If we carry it out further, the p and q square, this is q square, this Poisson bracket, I'm writing the result without carrying it out, but it's straightforward, you can check it. The q cancels, and this -2 taken to the other side becomes +2 -1, it gives you 1. So the final result is PQ is simply 1 by q square. And let us suppose we carry it out one more time. If you do that, then you will get, I'm simply showing the result, it would be 2 by QQ. That's it. So now it is time to write down everything. I mean, in the form d dot, if you remember, we had the p and then the Poisson bracket of q and h, which we found to be just equal to p, and then we have ph minus h. So this is p square by 2, simply because this is equal to p. And what about ph? Ph we started here, and here we found this is to be 0, and this one we found 2 by QQ. Okay, so minus half 2 by Q cube, and what else? We also have minus half, and that's it. But with it we have another factor. If we remember, we had half of pH and Q. Okay, so half of pH Q, and this is 2 by q cube and minus p square by 2 plus 1 by 2 q square, and it's clear that everything cancels, so you have 0. So that means we have just now proved that d is indeed an integral of motion. Okay. Now remember, I mean, in general, if you are asked that find out a Poisson bracket of this kind, then it is very tempting to expand FQ as a Taylor series and then argue that since Q and Q to the power n vanishes, so such an expression will give us 0. The only trouble with this Taylor expansion is you often do the Taylor expansion about Q equal to 0. But if you have a form of 1 by Q or 1 by Q square, a Taylor expansion about Q equal to 0 is not very wise, simply because that if at 0, at Q equal to 0, the function itself diverges. So, I mean, this is why we are not using the Taylor expansion. But if we had a polynomial or any other form where Taylor series expansion is fine, Q does not diverge at Q equal to 0, of course, this argument would be perfectly correct. You don't have to do anything. You simply set it to 0 because the FQ can be expanded using a Taylor series in Q. We would like to establish another very useful relation. You remember we already saw that the dynamical variables, particularly Q's and P's, their time evolution, which is Hamilton's equations of motion, can simply be written as, that's it, where U could be Q, any Q or any P. Now consider a situation where Hamiltonian is not a function of time. So which means del H del T is 0, and that implies we have already seen, because Hamiltonian always, the Poisson bracket of Hamiltonian with itself vanishes. So Hamiltonian is an integral of motion, okay, a conserved quantity. Good. So if we have such a situation, then what is U double dot, second derivative of U? Well, the derivative acts only on U and not on H, so this is what we have. But then U dot is already given, which is, that's it. So the triple dot will similarly be so for a dynamical quantity, the derivatives, the first derivative is one Poisson bracket with Hamiltonian, and then second derivative is two Poisson brackets, nested of course, one inside another with Hamiltonian. The third derivative is three Poisson bracket nested with the Hamiltonian. Now, in general, you can write U as a function of T using the Taylor series, of course assuming that U0 exists and the derivatives are all nice, I mean, which is usually the case. So we write down the Taylor series, which is U dot at time t equal to 0 plus t plus 1 by 2 factorial t equal to 0 t square plus 1 by 3 factorial. And so on and so forth. Now in this expression, this U dot, U double dot, U triple dot, we can simply substitute the above. But we'll have to evaluate it at t equal to 0. But then at t equal to 0, U has the value U0. So which gives us that we have U0 plus 1 by 1 factorial and similar terms. So you see, if we know the initial condition, then a dynamical variable, particularly Q's or P's, those can be written down for all foreseeable future using only the Poisson bracket. So this shows you actually how powerful the Poisson brackets are. In quantum mechanics, you will encounter a similar series known as Dyson series. That too gives you the state of the things, which we write in terms of what you call density matrix. Density matrix at time t would be exactly a similar series, except for Poisson brackets we'll have commutators and I and h cut those. But apart from that, the structure is similar. Density matrix on the right hand side will be at time t equal to 0. So this structure is universal both in classical mechanics as well as quantum mechanics. The Poisson brackets or commutators, they are powerful enough to give you the complete solution without solving any differential equation whatsoever. Just you have to evaluate the Poisson brackets, well, an infinite set of them, but in many cases these follow a pattern. Say for example, the double Poisson bracket can be written in terms of single Poisson bracket and so on and so forth. So as a result, the series are often not so difficult to evaluate, but in general it is a bit cumbersome, I admit. But the powerful thing is you do not have to write down the equation of motion or solve it. This is the solution. That's it.